you for the introduction. And it's nice to be part of this interesting workshop on the future of what you're going to do. And I want to talk today a bit about a project that we've been doing in Bremen about charge density waves. And okay. And the motivation actually sort of comes from two sets of experiments on tantalum disulfide, a material that we've seen a few times already in this workshop. These experiments are on a different polytype. I think most of what we've seen in the workshop was 1T tantalum disulfide, and these are experiments on 2H tantalum disulfide. And the interesting thing is that this material can have a charge density wave, but if it has a charge density wave or not really depends on how you do the experiment. So in the first experiment here, the tantalum disulfide was grown on gold and no charge density wave was found. And in the second experiment, the tantalum disulfide was grown on a layer of graphene which was on top of iridium, and in that case a charge density wave was found. And sort of the goal of this talk is to sort of try to explain from theory sort of the theory part of this paper and why there is this difference between tantalum disulfide on gold or on graphene on iridium, and how we should sort of understand this theoretically. And I should already also say that the charge density wave here is a 3x3 charge density wave. So not the Star of David phase that was visible this morning. Okay, so as theorists, we would like to understand sort of why there is this charge density wave and to understand the difference between substrates. And if you want to just understand a monolayer of a material, then density functional theory is mostly sufficient for this type of material. And you can do full ab initio calculations and the results are like on the right. So there you get the lattice structure, a top view and a side view. And you find that there is a band structure with one band close to the Fermi level and the other bands a bit further away. But clearly from the experiment, it's, the substrate is an essential part and we should somehow in our theoretical calculations also include a substrate. And one option would be to really do density functional theory calculations of a monolayer with a bulk material below. This was also the approach that was used in the first of the two papers that I showed previously, so the calculations on gold. But the disadvantage is that this kind of thing sort of escalates quickly because you need probably many layers of the substrate to model it accurately. And because the unit cells don't always line up nicely, you also need many atoms in the in-plane direction. And especially in the second example that I discussed, where you have a monolayer, then a layer of graphene, and then a substrate, you already have sort of three types of materials, and it quickly becomes too difficult to do anything useful. So we would like to do it a bit more efficiently, sort of to start from ab initio, but to treat the substrate in a more efficient way than a brute force calculation. And we would also like to understand what is happening. So it's of course good if you can find a calculation that really shows, okay, gold versus graphene makes a difference. We would also like to know what the mechanism is. And our approach to do this basically involves combining density functional theory for band structures of a monolayer with linear response calculations in density functional theory to get the phonon spectra and to get the electron phonon coupling, and then to have as a second sort of layer the substrate, where we can think about things like doping and hybridization, for example, and to combine these two into our final result. This is sort of the goal, to get this phase diagram. So what we would like to do is to really exploit the fact that there is only a single band close to the Fermi level, and that the expectation is that the single band is what is essential, and sort of support for this idea that the single band is really the thing that matters. Here are the phonon spectra of tantalum disulfide and tungsten. And you can see that they are quite different. Here there is a negative energy phonon mode, so this means that the system is unstable and the charge density wave arises. And here there's no such mode. And the only major difference between these two materials is the fact that this single band here is metallic and partially filled, and in tungsten, in the tungsten compound, it's completely filled, and therefore there are sort of no fluctuations there, and this is really the thing that causes the difference. So what we have done is to do a calculation of the phonon spectrum in a constrained way. This is the panel that you see in the middle, where the screening of phonons by electronic states here is taken into account, by electronic states here is taken into account, but the fluctuations in this space here are completely frozen. In that case, we see that the system is still stable, and this means that sort of the charge density wave has to arise when we include the additional screening coming from this single band here. So we have sort of a theoretical description that works in two steps or in two tiers, where we first downfold into a single band model and then calculate the phononic screening from the single band. And this is really, in this case, something that you can do exactly. So you can do sort of these two steps, one after another, and you will get this exactly the same result as you would get if you calculate the density functional theory phonons immediately. And this constrained density functional perturbation theory was introduced in this 2015 paper, and it is sort of similar in spirit to the constrained random phase approximation for electron-electron interactions that has been discussed a few times in this workshop. So the point is that electrons screen phonons, and this can be expressed in that sort of the new phonon spectrum is equal to the old phonon spectrum plus diagrammatic corrections, which include electron-phonon interactions at the endpoints and the propagation of electrons here in the middle. And these have a sort of typical expression that you find in these kind of susceptibilities. And here you can see why the single band at the Fermi level is so important, because the single band at the Fermi level has this sort of, here there's a difference of Fermi functions, and this is of course most interesting for something for a metallic band where the Fermi surface is crossed. And our idea now is that we can use this expression. If you use this expression just with the dispersion and the normal distribution functions that you get from DFT, you will get your sort of exact DFT result for the freestanding case. But instead, we can do modifications to the expression here. So for example, if we dope this, this metallic band, then doping just means that here we are shifting these two Fermi-Dirac distributions. And in the same way, it can be shown that hybridization of electronic states in the monolayer with the substrate can be encoded as Lorentzian broadening of this distribution function f. And what's sort of particularly nice about this is that we do sort of a single DFT calculation for the freestanding monolayer, and we can explore the entire environmental phase space really efficiently, because we don't have to do the DFT every time. We can just change the evaluation of these kind of Feynman diagrams. Okay, so what does this lead to? Well, here is sort of the first thing. A freestanding system would be here at 0.3, roughly. So low doping, no hybridization. And the spectrum of the phonons is as you've seen before. And you can see that there are negative energy phonon modes, and in fact, the phonon spectrum is really negative over a quite wide range of momenta. Now, when we move up, so here, this is where we are turning on additional hybridization with the substrate. What we find is that the energy of the phonon is raised, and here at this endpoint 1, the system becomes stable and the charge density wave phase ends. And what we can see is that here there was really a wide instability, and both 2x2 and 3x3 charge density waves were possible. But by hybridization, we can control and knock out the 2x2 charge density wave and have only the 3x3 charge density wave remaining, which is the last thing that becomes stable. At the same time, the system can be doped. Already in tantalum disulfide on graphene on iridium, there is some pseudo-doping of roughly 0.1, but it's possible to add additional lithium atoms to dope the system further. And this would mean that you are moving to the right in this phase diagram towards 0.4 here. And at 0.4 is where the charge density wave also sort of ends. But we see that 0.4 and 0.1 are different in the sense that the Q vector of the charge density wave changes. So in this region here, there are only 2x2 charge density waves. And finally, if we have both doping and hybridization, or if we have really sort of extremely strong hybridization, we find that this, the hybridization sort of broadens the electronic state. This makes these low energy processes that lead to the charge density wave, makes them less efficient, and no charge density wave is left. And this is where the tantalum disulfide on gold experiment, sort of, this is the regional phase space where that experiment occurred. So in this way, we can understand the sort of the difference between the two experimental STM results, namely the difference is both doping and hybridization. And in fact, this part of phase space, lithium doping to go from 3x3 to 2x2, could also be done experimentally. So you see here 2 images, and here there is 1, 2, 3. So it's the 3x3 charge density wave, and here it's the 2x2 charge density wave. And the difference is the lithium doping. So we have sort of a successful ab initio theory to understand really experimentally observed differences depending on substrates, without needing to go to a really extremely detailed and optimistic description of the substrate. A few parameters are sufficient to understand what's happening in all of these experiments. But we can do more, because I showed you sort of this nice Feynman diagram, and we evaluate it to get the results that we want, but we can also learn something from it. The Feynman diagrams are, as usual, sort of a sum over internal variables. In this case, the main internal variable is the momentum, the electronic momentum, because there's only a single band, so we don't need to work a single relevant electronic band. And we can look which momenta are really responsible for the largest contribution to the sum. And this will, in this way we learn what is the mechanism that is responsible for charge density waves. This is something where sort of there were a lot of different opinions and a lot of papers have been written suggesting, for example, von Hove singularities as being responsible, or nesting, or matrix elements, or and so on and so on. And we really have a way to say what is the true answer to this question, just by looking at looking at the summand part by part. For example, if it's a von Hove singularity scenario, you should really see that the summand is strongly localized exactly at the von Hove singularity, while if it's nesting, you should see rather large portions of the Fermi surface that are responsible. And this kind of technique to investigate which fluctuations are responsible for the observed physics is something that was done in the case of electron-electron interactions, especially in the Hubbard model and in low dimensions, already a few years ago in a paper by Gunnarsson et al. And our idea here is basically to use the same kind of technique for electron-phonon problems. And at this point, it's maybe useful to say that there is a bit of a difference here. When you are looking at the self-energy of an electron-electron interaction problem, you will typically find contributions with positive sign and with negative sign that compensate. And this compensation can really be extremely sort of substantial and relevant. So the fact that contributions with different sign cancel is usually important. Here we are a bit sort of more lucky that the expression here is really positive definite, and that we are summing positive elements, and that we can really say a specific momentum is responsible for 10% or 20% or 5% of the total effect. Okay. So I have a few pictures to illustrate this. They are a bit complicated perhaps, but I will try to talk all of you through them. So what's shown here is this phonon self-energy, the thing that we are interested in, for a specific Q vector, so this one here, and without any doping, decomposed in terms of the electronic momentum K in the Brillouin zone. This is the Brillouin zone. Here is the Fermi surface, and here these are the thick black lines. But in the expression for the phonon self-energy, let's go back maybe, we see that there are always two relevant momenta. There is K and there is K plus Q. And the dashed lines are showing us the Fermi surface translated by Q. And in the picture, we see that here there's really a single small region where, where everything is coming from, and everything else is sort of blue and means it's approximately zero. And this region is where the original Fermi surface and the Fermi surface translated by Q sort of are nicely aligned. And we can look at the two different parts that contribute. The first one is the purely electronic susceptibility. And we see that it's indeed large whenever two Fermi surfaces meet. This is also what you sort of expect. So this means that the Q vector transfers an electron from one Fermi surface, one part of the Fermi surface to another part of the Fermi surface. But there is a lot more red here than in the picture at the top. So purely fermiology and Fermi surfaces is not enough to understand what's going on. The second ingredient is the electron-phonon coupling, and here I show G squared, which clearly is sort of localized in, well, a single spot here and symmetrically a single spot here. And it's the product of these two that ends up being the phonon self-energy, and ends up being really localized in a single spot. And we can see the same thing also if we take a different momentum transfer Q. So we again see a single hotspot, which comes from the combination of Fermi surfaces and electron-phonon coupling. So yeah, this means that both purely electronic effects and electron-phonon coupling are important. And what we would like perhaps, okay, so this we understand, the susceptibility that it's peaked where Fermi surfaces meet, but we would also like to understand a bit better why is the electron-phonon coupling so localized in momentum space. And it turns out that this can also be understood from a relatively simple view, namely that the K pocket here is sort of like massive Dirac fermions. So there's the K pocket where there are sort of these two electronic structures. And the electron-phonon coupling is between K and K prime. And at K and K prime, the orbital content of this band is different. And this means that normally if you would look at electron-phonon coupling, you would just think about a Fermi velocity, and a Fermi velocity would just be a vector in K space, which is sort of pointing outwards from the Fermi surface. But in Dirac pseudospin physics, all of these things are two-dimensional 2x2 matrices. And this means that the Fermi velocity is a matrix as well, and that when you compare the Fermi velocity at the K and K prime point, you not only have to take into account sort of the energies, but also the fact that the matrix structure is changing between the two. This gives you an expression like the one on here, which has a projection on a single component and then compares the K and K prime point. And this sort of relatively simple view gives a picture like this, which is similar enough to the actual full ab initio results that we found in the previous slide. Sort of there's a single hotspot where the matrix element filter is effective, and this was also what you could see here. So I would like first to conclude a bit and then to talk about perspective and relations with what's going on in your projects. So we can do the ab initio calculation of these kinds of problems, and we can really find sufficient accuracy to explain differences seen in experiments. And it's really something where there is really real interplay between electrons and purely electronic phenomena and electron-phonon coupling. And this can be done efficiently via low energy models, where the concept of downfolding to a few band model allows us to parameterize all environmental effects and do efficient but still accurate calculations to see what the environment really does. And this kind of low energy intermediate model is not just sort of efficient, but also helpful to understand what is going on, because we have this sort of fluctuation diagnostics as a tool to really find what is going on. And in this particular example, for example, we found that the way to think about this material is as having Dirac pseudospin textures. And this is something that you might be able to, I don't know, if you're smart enough, you might be able to guess from the start, looking at the band structure, that this is going to be relevant, but it's not so easy to to find what electron-phonon coupling would be like in that case, and if this is really an appropriate model. And here, by doing the entire theory from ab initio, via a low energy model to the final results, we are able to control all of these steps. So I think, these are some nice features of the theory that we've been developing. And looking at sort of future perspectives and also relation to previous talks in this conference, I think the most important issue is that most of what we've been seeing for electron-electron interactions is happening in effective low energy lattice models. And our approach here is basically doing the same thing and using many of the theoretical ideas like constraint theories, like fluctuation diagnostics that first made their appearance in electron-electron theories. So they provide sort of a nice starting point to try to combine the effect of electron-electron and electron-phonon interactions in a, let's say in a universal theory, and in this way to try to understand, for example, if how electronic correlations and lattice ordering phenomena, how they are related and how they influence each other, because we've seen charge density waves, for example, in Matteo's talk earlier today. Those were entirely electronic charge density waves. These are entirely electron-phonon charge density waves. And it would be good to understand them in a sort of uniform way and to see how much feedback there is between these kind of fluctuations. Okay. The main theory of this is contained in this paper, and this is also, so Jan Berges is the student who did most of the work on this, and the other people are Arne Schaubert from Bremen, Malte Röstner from Radboud University, who has also given a talk in this workshop, and Tim Wehling. And the experimental work was this larger collaboration, which with the Cologne groups. And I would say that, I'm more or less finished, so I would say that we now have time for questions.